Hello, everybody, and thank you for tuning in on this video poster. I am Andrea Sangiovanni from the University of Trieste, and today I'll talk about OpenString methods and Gopakumar-Vafa invariants, basing myself on work in collaboration with Andrea Scolinucci, Roberto Valandro, and Mario De Marco. The overarching theme of this poster will be the close relationship between stringing methods and topological invariants. The punchline is that we can get inside and concretely handle computations of physically relevant mathematical objects, such as topological invariants, by using string theory techniques, thus also getting information about the physical origin of such objects. The outline will be the following. I'll first explain what exactly are these Gopakumar-Vafa invariants, known for friends as GV invariants. Then I'll go through why we are interested in counting them. This is the motivation. And the main part will be devoted to explaining a new idea to find an easy and physics-based way of computing the so-called genus zero GV invariants for a class of non-toric Calabi-Yaus. So let me get straight to the first point. So what exactly are these GV invariants? They are topological invariants, meaning that they do not change under homeomorphisms, and they characterize Calabi-Yau spaces. Now, we can define them, roughly speaking, in this way. Consider a Riemann surface, sigma g, of some genus G, a Calabi-Yau threefold X3, and a two-cycle beta inside this Calabi-Yau. Now we ask, how many holomorphic maps can we build from the Riemann surface sigma g to the two-cycle beta inside the Calabi-Yau, as you can see in this picture? The answer is that we can count these maps with some numbers called n beta g, where beta is the two-cycle and g is the genus of the Riemann surface. And we call these numbers Gopakumar-Vafa invariants. This will be our main objects of interest. And in the following, I'll focus especially on genus zero GV invariants and beta zero, meaning that the Riemann surface is just a sphere. Now, the question is, why do we care about this kind of objects? What are they useful for? The point is that n beta g give the number of BPS states of M2 branes wrapping the curve beta inside the Calabi-Yau. And to give you an example of this, we have that n beta 0 gives instantaneous corrections to the kernel potential in type 2 theories, where we have the usual perturbative contribution and then an instantaneous correction that depends on these GV invariants. So this is an example of why we want to characterize the GV invariants of Calabi-Yau spaces. The main question now is, how can we do this? How can we compute these GV invariants? There are existing techniques in the literature, and now I'll explain a new way, a more physics-based way of doing these computations. So we are interested in the following in singular non-toric Calabi-Yau threefolds that arise as one-parameter families of deformations of ADE singularities. So this was a long string of words, and so I'll explain every part so that we can exactly understand what's going on. So let me focus on the ADE singularities part as a first. So ADE surfaces are singular spaces that are classified in terms of the exceptional divisors in their resolution. So for example, if we have this AN equation, we can see that this geometry is singular at the origin, and that if we resolve the singular point, we find a chain of NP1s arranged in this way that you can see on the right. In the following, I'll actually consider singular threefolds where only one of the P1s can be blown up, and these are called simple flops. Actually, here I have shown you a twofold because we have three variables and one equation, but we want threefolds. We can obtain a threefold by deforming ADE singularities, adding terms depending on a single parameter, let's call it W. For example, for the conifold, we just have an A1 singularity with some deformation depending on W. We can see that this equation is a threefold, that it is singular at the origin, and that there is a single P1 that can be blown up at the origin. Now consider M theory placed on top of one of these singular threefolds that arise from one parameter deformed AD singularities. Then Witten has taught us that if we dimensionally reduce M theory on this Calabi-Yau, we obtain a 5-dimensional theory where there are hypermultiplets that descend from the M2 branes wrapping curves in the Calabi-Yau. So as you can see in this picture, we have M2 branes on the Calabi-Yau that descend to hypermultiplets in the 5-dimensional effective theory. The states of these hypers are exactly what we want to count in the following, because we will see that they are in one-to-one correspondence with the GV invariants of the Calabi-Yau. So how can we do this? We must first use a trick. So we rewrite the threefold in the form of a C star fibration. So in this shape, UV equals the determinant of some matrix T that I'll define in a second. So for example, for the conifold, we have that, but just by changing variables from X and Y, we go to U and V and we obtain the desired form. The relationship then is the following. We have M theory built on this threefold, UV equals determinant of T, of this matrix T. And on the other side, by reducing on the M theory circle, we get the type 2A theory with the 6 branes placed on top of the locus determinant of T equals to 0, which is where the C star fibration degenerates. In the following, I'll focus on the right-hand part, so on the type 2A side of things, focusing on these 6 branes. The last question is, what is this matrix T that I've introduced? The answer comes from the Tachyon condensation formalism, which roughly speaking says the following. We can consider a stack of D8 branes and a stack of anti-D8 branes connected by tachyonic strings that we can describe with a tachyon matrix. Physically, what happens is that these two stacks can collide, they are unstable, they collide and they can annihilate. If the tachyon matrix is of some specific shape, there can be some D6 brane setup that remains, as you can see in this picture here. So the tachyon is just a matrix, a map between vector bundles E and E tilde that are built on the D8 and anti-D8 stack. And now our objective is to compute the open string states in the D6 brane system that is left over after the D8 and anti-D8 annihilate each other. So just to recap what I've shown you so far, the strategy to compute the GV invariance is the following. Consider Calabi-Yau threefolds defined as one parameter families of ADE deformations. Then use the M theory and type 2A duality to give a description of the corresponding D6 brane system. Then build a tachyon that describes the this D6 brane system and compute fluctuations of this tachyon that correspond to the open string modes. Finally, we will identify these open string modes with the GV invariants of the Calabi-Yaus that we have started from. So let's see how this works briefly in a concrete example. The example is the one of Reid's pagodas, which are a generalization of the conifold. They are defined by this equation, which is a deformation of an A2K minus 1 singularity. It is singular at the origin, and we can see that there is only one P1 in the resolution. Now we want to rewrite this equation as a C star fibration. So we just change variables and obtain a form UV equals the product of these two factors on the right. And now the last step is to find the tachyon, that is a matrix T, such that its determinant is equal to the product of these two factors. It can be shown that the minimal tachyon that does this work is the one depicted here, because its determinant trivially reproduces what we want. Physically, what we are doing is describing a system of two branes, each one corresponding to one of these factors, that intersect each other on a single point defined by z to the k equals to w equals to 0. And what we want to do now is to compute the open string modes between these two branes. We do it by considering fluctuations of the tachyon and performing the explicit computations. What we find is that there are two k modes that correspond to k hypermultiplets in 5 dimensions. So the physical situation is depicted here. We have strings stretching from one brane to the other near the intersection point, and we find 2k of these modes. They correspond to k hypermultiplets in the 5-dimensional effective theory. On the other hand, the GV invariants for this kind of geometries are as follows. We have that n0 of the referred to the class of the exceptional P1 of the Reid's pagodas is equal to k, and all the others vanish. So we see that there is a perfect agreement between the number of hypermultiplets and the GV invariants of the geometry. So this is the correspondence that we wanted to see. This is the result that we achieved. So to sum up, what I've shown you so far is that the Tachyon is a multi-purpose tool that allows us to find a physics-based way to compute genus-zero GV invariance for a wide class of non-toric Calabi-Yaus in the AN series, in the DN series, with simple flops or non-resolvable singularities. There are many examples that I've not shown you. And also we can investigate the structure of the X branch of the 5-dimensional theory that arises from dimensional reduction, thus allowing a check with existing results. For the future, we have in mind to study multiple flop singularities, to investigate the switching of t-variant entries, and finally to apply this technique to more involved single flop and non-resolvable singularities, thus connecting with existing works. This will be everything from me. Thank you very much.